In this video, let's look at the structure and bonding that takes place in ionic solids. Within the BOB textbook, 12.5 ionic solids, the description is, let's examine the structures and properties of solids held together by mutual attractions between cations and anions, and learn how the structures of these ionic solids depend on the relative size of the ions and their stoichiometry. So let's look more deeply at those ideas. So BOB moves into a description of ionic solids by connecting it back to a previous treatment of these. Back in chapter 8, that's where we were looking at the formation of ionic bonding. Topics like lattice energy were first introduced there. The Born-Haber cycle was found there. So the first thing that the authors do is say, let's look back and revisit those ideas. Let's see how aspects of the lattice energy leads to connections with things like melting point. So if you recall, for the lattice energy, a larger lattice energy corresponded to when we had larger charges on our cations and anions. And sort of as a tiebreaker, if the charges were the same, like I see right here for these different compounds, the smaller sizes would allow those charges to get closer together, and that would lead to a larger lattice energy. That's how I would be explaining the melting point that I see here back in chapter 8. Another feature that we have when we're now thinking about the properties here of the ionic solids, so it points out something that is interesting, how both ionic and metallic solids have high melting points and boiling points, but there are differences in the bonding that leads to other properties being different. I think this is really valuable conceptually. We don't simply have one way that we can end up with high melting and boiling points. There's different ways that we can have the charges arranged, whether they're localized within our ionic compound or delocalized in the metal, and still reach that same description. The idea of having them localized versus delocalized, well, that gives rise to different properties. It makes them brittle. This is one that we typically show of what does it mean to apply a force and take arrangements that had initially been positive, negative, all in a favorable array to an unfavorable one that would cause it to cleave. Gemstones, the fact that you can cleave them, a jeweler can cleave them across particular planes, are ionic compounds like this. There's also a description here of how they would be electrical insulators rather than electrical conductors. Students comment within this that they made within perusal, how they remember that in previous classes they'd been given some of these properties, but they'd never seen it, as they say, broken down to the particle level. Descriptions like this they found quite helpful. So how is our ionic solid constructed? Well, like any crystalline solid, we'll have a motif that's combined with the crystal lattice to lead to the crystal structure. So on the left-hand side, these would be for ionic compounds, on the right for metals. Key difference there is the motif. For an element like gold, the motif can be a single gold atom that we then combine with the crystal lattice to get to the crystal structure. But for an ionic compound, that clearly can't be the case, because we need to have more than one type of a atom present within the solid. So our motif has to be used that when it combines with the crystal lattice, the motif that we use, it needs to be more than just a single atom. Now, if I look at the ones that I'm combining then, if I think back, cations are smaller than anions, so that's what's being shown within this representation too. That was an aspect that we saw back in chapter 7 when we were looking at periodic properties of atoms. Now, this idea that you can often visualize the cations as being found in then the holes in the structure, I really see that here with the sodium chloride structure. It's as if I'm taking the chloride anion, which is larger, and I'm putting it at all of the different lattice points in the space-centered cubic. And then in the resulting hole that's next to each of those, in the smaller space there, that's where I put the cations. So a lot of times, because the anions are larger, in a way they dominate the structure, they give an initial framework, and then we can consider where the cations then would be found within that. Now, within this description right here, points out that these are common ionic structure types. This is more far-reaching than it might seem. when it comes to ionic structures, there are some very standard ones that an inorganic chemist, they just refer to. They'd say, oh, this is the sodium chloride structure. That doesn't mean that only sodium chloride adopts this and they're only interested in sodium chloride. It means that there are many other ionic compounds that adopt the same structure. That sodium chloride structure, sometimes you see referred to as the rock salt structure. Or the zinc sulfide shows up and it's referred to as zinc blend. Now, and that's how it's always spelled. Okay, it's like the fish and chips shop with PPE. It has that E ending on it. So if you want to be in the know when it comes to ionic structures, you can refer to the zinc blend. Now, the factors that are resulting in a particular shape here, a particular crystal structure, it has to be able to account for the stoichiometry, and it has to be able to accommodate the relative size of the ions that we have. So, in a way, this is why we don't have an infinite number of crystal structures for these different ionic compounds. We know from our own experience when it comes to the stoichiometry, we don't have an infinite number of combinations of cations and anions. I mean, I guess we could, but we see so many times, oh, it's a 1-to-1 ratio. It's a 1-to-2 ratio. The simple empirical formulas, okay, it makes sense that we don't have that many different empirical formulas that we need to account for when we're looking at ionic structures. Second, in terms of the size, we're going to see there's particular reasons that the size of the cation and anions lead to particular crystal structures as well. So this is a long way of saying that when there are certain structures that are found, certain ionic structures that are found, it's going to make sense why we have a small number of those instead of a very large number. So here's a table from the Brown-LeMay Burston textbook. This is looking in more detail at the cesium chloride, the sodium chloride, and the zinc blend structure. So first feature I take away is it's describing the coordination number for the cation and the coordination number from the anion. Coordination number, that's how many immediate neighbors it has. So the cation in sodium chloride, it has 6 immediate anion neighbors. The anion, it also has 6 immediate closest cation neighbors. So one thing that I take away from this is when the stoichiometry is 1-to-1, the cation to anion ratio in the empirical formula, the coordination numbers are going to be the same. Now, what if they're not? So here I show data for examples where in our empirical formula it's not 1-to-1. Lithium oxide, magnesium oxide. Notice how the coordination numbers now change. One way that we can make sense of this, one pattern that we're going to see, is if we look at a relationship between the charge of the cation and its coordination number, that ratio, it matches the charge of the anion and its coordination number. So if I take the scandium oxide, I have a +3 with a coordination number of 6. I have a charge of 2 on the oxygen, coordination number of 4. This pattern, that works for all of these examples that we have right here. If I look in the textbook, Inorganic Chemistry by House, this is that same description of what's going on. It points out that when you have a 1-to-1 compound, 1-to-1 ratio in the empirical formula, it means that you have to have identical environments around the cation and the anion. In that 1-to-1 compound, they also had the same charges. It goes on to describe what's called the electrostatic bond character. What happens if they're not 1-to-1? Notice that they're putting bond here in quotes. There's not saying that there is a distinct single bond of some type between the cation and anion. It's instead talking about the overall environment around it. What this is saying right here as we think about distributing the charge is the ionic compound as it goes through, it's homogeneous. It's not like, oh, over on the left side of the ionic compound, we have more positive charge, and on the right side, there's more negative charge. Our balancing of charges extends throughout the entire compound, and that's reflected in the differences here in the coordination number. So let's see how it begins to fit together. So here we see a description for calcium with fluoride anions. So let's put into practice some of our skills here. Let's, based on inspection, see if we can come up with an empirical formula and then think about what the coordination number would be for the cation and the anion. So when I say the empirical formula by inspection, I'm just going to look at that. I'm going to see that I have 2 calciums within the unit cell. For the fluoride, I've got to do a little math here. I have 8 that would each have a 1/8 contribution, 2 that are found on the faces that would all be 1/2 as they're shared with a neighboring unit cell, and 8 that have a 1/4 contribution as they'd be found in 4 unit cells. Adding that all together, okay, it works. Calcium fluoride has 2 calciums per unit cell, 4 fluorides, leads us to the empirical formula that we would have anticipated. Now, what would be the coordination number? I think I can look and see this calcium that it has 1, 2, 3, 4, 5, 6, 7, 8 neighbors right around it. So the coordination number for the calcium would be 8. Now, it might not be as obvious what it would be for the fluoride. We sort of have to imagine what would the neighboring unit cell look like. But we can come back to this approach right here. Calcium's plus 2 with a coordination number of 8. The fluoride's minus 1. Its coordination number must be 4. And now if I want to sort of rationalize that, if I look back at this one right here, I see that it has 2 within this unit cell, and it would have 2 within the neighboring one. That's how it ends up with the coordination number of 4. It's all fitting together. Now, another feature that I have right here is data as far as the size of the cation relative to the size of the anion. As that ratio changes, I see that the coordination number is changing. This is the idea within that. The cation must be large enough to keep the anions apart from each other. If we have it so it's large enough, it could keep those negative charges apart from each other. The stability limit is saying, okay, at what point can the cations just occupy enough space to keep the anions apart from each other? Because if the cation becomes even smaller than that, yes, there's a vacancy there, but it's now bringing the negative charges too close to each other. So this is a way of saying that the relative size of the cation to the anion is going to affect the coordination number. If it can't keep the negative charges with 4 of them separate from each other, the coordination number would go down, and it could keep 3 of the anions apart from each other. Here's some general groupings then as far as showing you how, if we look at that particular ratio, we have a description for what would be the coordination number of the cation and what would be the resulting shape that we have. So it's beginning to fit together now. We're looking at the cations and anions. We can imagine them to be these charged hard spheres, and we're seeing what does it mean as we're putting them together. So let's see how this now fits together with another very common crystal structure, the rutile structure. So here is 2 different representations for that to help us sort of visualize what's going on. So first of all, let's analyze this ionic compound. Let's see if we can think about the empirical formula and then make sense of the coordination numbers. So in order to come up with the empirical formula, let's get that by inspection. Let's look at the images here and see what we come up with. So for the titanium within here, I see that I have 1 in the center and I have 8 on the corners. That tells me that I have a total of 2 titanium atoms within the unit cell. For the oxygen, it's going to be helpful, I think, to use both of these representations. I have 2 that are found entirely within the unit cell, and a total of 4 that are on the faces. 2 that are in the unit cell, and a total of 4 that are on the faces. TiO2 would be the empirical formula then. Let's see if it makes sense then in terms of the coordination. So the titanium is going to have a charge of 4 with a coordination number of 6. I can easily see that in this case right here. 1, 2, 3, 4, 5, 6 neighbors around that titanium. The oxygen has a charge of 2, so it must have a coordination number of 3. A trigonal planar, I can really see that for this oxygen right here. 1, 2, three neighbors, trigonoplanar geometry. If we were to grab some data for that, titanium 4 plus, the size for that cation is around 70 picometers. The oxide anion around 140. Going back to that table, that gives me a ratio. I can do the math in my head on that one. 0.5, coordination number of 6 for the cation. That's exactly what we had within the structure. Now, pausing for a second, it's always nice when an approach explains many things. Look at all these ideas that just came together here. We were able to look at the unit cell and make sense of the empirical formula. See how the empirical formula and the unit cell, they have to be leading us to the description for that ionic compound in terms of its stoichiometry. We have a description of what the cation environment is. What is its charge? What are its neighbors? Same thing with the anion environment and how those can be described in terms of the coordination number. So many things are fitting together cohesively within our description here. Here's just another example. This idea of let's look at it based on inspection, come up with an empirical formula. This is one that I would practice with my students. This is a typical learning objective that we have. This is one involving nickel and arsenic. Part of the reason we're picking this one, we don't want to have one where it's obvious to the student just based on the periodic table. If we ask, well, tell me about the empirical formula for sodium chloride, they already know that one. If we want to have them actually go through the process of inspecting the unit cell and coming up with an empirical formula, I think we have to do two things. We have to do one that they're not familiar with, and two, we have to provide good images that would allow them to determine what's going on. So within this one, if I add it up, I can see that I have nickel at the top and the bottom here that would have 8, all with a 1/8 contribution, 4 that are along the edges. That puts a total of 2 nickels within the unit cell, and within the arsenic, I can definitely see if I combine both of these that I have 2 within that. So it's a 1-to-1 ratio within the empirical formula. Now, turning just momentarily to the bonding here. This is from Atkins, where we have a description of the bonding in an ionic compound. Atkins is all about coming back to let's think about the Coulomb potential energy. So he gives a description of that. We have our fundamental charge, E. We're combining the charge of one ion, charge of the other, so the charge of the cation and the anion. And we have a description for the distance here, the separation of those. The idea that this is now describing the total potential energy that we have within the ionic compounds. Because one of the charges is positive and one's negative, it leads to a negative potential energy, so that's making sense. There's this idea that the repulsions and attractions, they become progressively weaker as we move further and further away. So initially we had an attraction followed by a repulsion, attraction, repulsion. It's not that they're all equal to each other. They're not equal. Sometimes students have that misconception. They can't be equal. If they were all equal to each other, we would have no net decrease in the potential energy. But we do because overall, the favorable attractions are greater than the unfavorable attractions. Another student comment within perusal. This is another aspect of ionic bonding that I need to wrap my head around. Previously, I thought that a solid made of these elements, like calcium chloride, would be these calcium chloride molecules that are stacked together. Instead, Atkins is telling us that it's only showing the ratio of the atoms found in the sample, ? Would the negatively charged chloride anions still surround the calcium 2 plus anions in all sides? Really insightful comment within here as they're trying to make sense of what do we mean when we're thinking about this extended solid with these alternating positive attractions between positive and negative, and then repulsions that then follow within that. Now, Atkins gives a description so how we can begin to think about this in a very simple system. If you were just to have these alternating charges all in a line, a one-dimensional crystal, and shows how that you can construct what the resulting pattern would be. And when I say pattern, what the resulting factor would be, which is called the Madelung constant, that's based on the geometric arrangement that you're considering. And in this case, it's a one-dimensional crystal. He shows a little bit of how you can calculate this. how you derive that, or as he says, how this is done, where you have these alternating attraction, then repulsion, then attractions, repulsions for this model system right here. It ends up having this series that's ln of 2, and it gets doubled because he wants to think about it both going in the left and the right directions. So in order to sort of illustrate this, I made a graph of these contributions. So I took this value right here and doubled it, doubled it, doubled it. So we see, first of all, a value of 2, value of -1, plus 2/3, -1/2. This would be for this model system. And sure enough, if you look at those and say, let's combine the first, and then the first and the second, and then the first, second, and third, what you find is that it's converging right along this value that he described. Now, that's why he's saying that these repulsions and attractions become progressively weaker. Much of the story was right at the start, and then it becomes less and less, diminishing returns as you move on. Looking just a little bit more closely at this description of the Madelung constant, I grabbed a couple images here from a new textbook by my colleague Pat Woodward involving solid-state materials chemistry. So it's showing if we're looking within sodium chloride, we have initially our neighbors that would be attracted, then a repulsive term, then attractive as we move further and further out. Here's his description, and here's the resulting description for where you initially have attractions, then repulsions, and attractions, and we step through. So within this one, when I see this series, and you'll see this many times, it leads to different Madelung constants depending on the geometry of how you've arranged it. The sodium chloride structure has a different one than our friend the zinc blend there, or the rutile structure. Different geometric factors, different Madelung constants depending on how those charges are arranged. Now, what does this pattern look like? It's easy to take these then and make a plot, so that's what I did. Before that, I made a guess. I said, okay, this is going to look like that 1D description. My initial guess would be, okay, you've got overall attractions, then some repulsions, and you see that you have diminishing returns. I thought it would look something like this. I predicted it would be converging in the same way if we looked at our neighbors as we move further out. But if you actually then plop this into Excel, make a plot, this is what you actually see. It's more complicated than that. In that linear example, notice how we moved further and further out, and we always had the same number of neighbors as we kept moving out. If we were going both in the left and right direction, we would initially have 2 attractions, then 2 repulsions, then 2 attractions, 2 repulsions. But in our crystal structure, it's more complicated than that, because as we move further out, yes, they're farther away, but we also have more of the particular particles that can be found in that zone. And if you're looking at it overall, it's a lot more complicated. That's why Woodward and colleagues describe it this way. They point out that this series right here, it does not readily converge. It's not a mathematical function to say, oh, this easily converges. Because as we successively move further out, we do have anions and cations that were found there, but their numbers are changing in a way that doesn't make it as easy as that one-dimensional description. Sure enough, if you construct your spheres, if you make it so as you move further out, you're not looking simply at the distance, but you're also trying to make them neutral clusters as you move out. That's how you can make it so the math works and it converges. Now, is this a crucial feature? No, it's not. But I will point out that this is a misconception of my own based on the simple linear description that Atkins provides. It's more complicated than that. It still works, okay? You still have a Madelung constant for this, but it's not a simple derivation. So wrapping up here as we think about our features for ionic solids, I come back to the same statement. It's always nice when an approach explains many things. Notice all of the parts that were coming together for the structure here of our ionic compounds. Empirical formula, the unit cell, the environment around the cation, the anion, the coordinations dependent on the size of these, the cation to anion ratio, consistency within the coordination numbers and how we could predict different things. To me, it's really powerful. I know we go through a whole series in general chemistry of let's draw a Lewis structure, let's use VSEPR to predict the geometry, let's talk about now molecular polarity. Now let's think about the intermolecular forces that would be present. There's a lot of different parts that we put together within that whole description. There's a lot of parts within this one, and to me, this is almost more easily accomplished. It's more easy to see how these different features fit together. So it really empowers me to think, okay, I know something and I can make predictions involving ionic